Welcome back to The Explainer. Today, we're literally going to shatter your everyday perception of the physical world around you. We're going to pull back the curtain on what's really happening right in front of our eyes. Get ready, because things are not exactly what they seem.
Okay, let's just dive right into this by challenging your immediate physical surroundings. Take a second and really think about the solid chair supporting you right now, or maybe the screen sitting right in front of your face. To our very human senses, they represent the absolute definition of solid, right? They seem perfectly stationary, absolutely silent, and completely stable. But are they actually still?
Well, the short answer is absolutely no. What our limited human senses are telling us is, quite frankly, a clever biological illusion. Beneath the surface of every single object in the universe, everything is in a constant state of frantic microscopic agitation. It's a phenomenon we're going to call the invisible dance.
Let's move into Section 1, the Great Biological Illusion, shrinking our perspective.
So the absolutely crucial point here is that matter is fundamentally discontinuous. It is not a solid continuum like it appears to our eyes. Instead, it's actually a collection of discrete entities. Individual building blocks like atoms, molecules, or ions. And here's the really wild part. Even in a solid, seemingly unmovable rock, those fundamental building blocks never ever stop moving. They are in a state of perpetual agitation.
All right, moving right along to Section 2, Rules of the Dance, looking at the kinetic theory. To actually make sense of all this microscopic movement, we turn to the kinetic theory of matter. Think of this as the master rulebook. It details the specific parameters that govern literally all material behavior, from that screen you're looking at to the very air you're breathing right now.
Breaking that rulebook down, we get the 4 pillars of kinetic theory. First up, composition. Matter is made of minuscule, discrete particles. Second is motion, meaning these particles exist in a constant, random, and completely restless state. Third, we have thermal influence, so temperature directly dictates their velocity. And finally, the 4th pillar, structural forces. Matter is actually full of hidden gaps, basically empty spaces, and it's held together across the void by attractive forces.
Which brings us to Section 3, Choreography of the states, solids, liquids, and gases. As we zoom in a bit further, the choreography of these particles shifts dramatically depending on the specific state of the matter we're looking at. In solids, you've got closely packed particles just vibrating in fixed positions, creating very low compressibility. Then in liquids, they're still close together but much more disordered, freely sliding past each other. And then, of course, in gases, they are far apart, moving super rapidly, which creates incredibly high compressibility.
Now, what's really fascinating here is how human engineering perfectly exploits these different states. Think about hydraulics for a second. They use the low compressibility of liquids. Because the particles are already tucked tightly against one another, they violently resist being forced into smaller volumes, and that is exactly what allows for instantaneous power transmission. Pneumatics, on the flip side, leverage the vast hidden gaps found in gases. We're literally squeezing those far-apart particles into small containers, which gives us amazing energy storage and shock absorption.
Let's jump right into Section 4. The atomic speedometer, redefining temperature. To fully grasp this restless framework we're talking about, we have to address what actually drives the speed of this microscopic choreography, and that's thermal energy. In the industrial and microscopic world, we have to completely abandon our subjective idea of hot and cold. Actually, scratch that. It's not even an idea, it's just a feeling. Real temperature is actually a direct, rigorous measurement of particle velocity and mean kinetic energy. Basically, a thermometer is secretly just a speedometer for atoms.
Think of it like this. High temperatures mean a system has absorbed thermal energy. This triggers an absolute atomic frenzy with faster, harder collisions, which naturally drives up the pressure. Conversely, low temperatures just mean that kinetic energy has bled out into the environment or maybe an adjacent system, significantly slowing down the particle's pace.
This internal particle speed facilitates mass transport, which actually brings us to a really fascinating question about everyday life. I mean, think about it. How exactly does the scent of perfume cross a perfectly still room without the help of a breeze or a fan?
Well, the answer is diffusion. It's the spontaneous movement of particles from high to low concentration. This happens fastest in gases, simply because the particles can navigate the mostly empty space with incredible speed. It's noticeably slower in liquids due to crowding and resistance, and it's almost non-existent in solids. So the fact that someone's overpowering cologne hits your nose from across a completely still room, that is living, breathing evidence of these invisible particles constantly bouncing and sliding through the hidden gaps of our world. Moving right along to Section 5, the bond factor, temporary shifts versus permanent transformations.
So beyond just moving around or speeding up, we really have to look at what happens when these restless particles fundamentally change who they are. The bond factor is our crucial dividing line here. It determines whether a shift merely overcomes intermolecular forces, meaning the particles just shift their physical state, or if it fundamentally rewrites a substance's chemical identity through the actual breaking and forming of molecular bonds.
So how do we actually distinguish these changes in materials engineering? Well, it really comes down to a few key factors. Physical changes are usually reversible and require very little energy to achieve. Chemical changes, on the other hand, form entirely new substances. They're usually completely irreversible, and they require a massive energy shift. Let's put this theory into practice and contrast ice melting with iron rusting. Ice melting is a simple physical change. It requires a relatively small energy input to simply overcome those intermolecular forces we talked about. It loosens the particles up so they can move more freely, but at the end of the day, it's still just H2O. Rusting iron, however, is a full-blown chemical change. It requires massive energy to manipulate the actual bonds between the iron and oxygen. It creates a completely new, incredibly brittle oxide layer that entirely destroys the structural integrity of the original material. No going back from that.
And finally, Section 6, Seeing the Restless Sea, a New Perspective.
Understanding this kinetic and chemical framework isn't just some dry academic exercise. It's the absolute foundation engineers use for predicting material fatigue, assessing durability, and successfully building the macroscopic world all around us. I'm going to leave you with this provocative thought directly from our source material. Now that you know about this restless microscopic sea, the hidden gaps, and the buzzing hive of activity inside even the most rigid structures, if you could truly perceive the atoms in your morning coffee, would you ever see the world as still again? Thanks for joining me on this explainer. Keep questioning what you see and keep learning.